A faint signal, no one knows where it came from, appeared for 6 seconds over a quiet section of sky where no stars should speak. Days later, astronomers studying 3I Atlas noticed a pattern hidden in its light curve, a pulse repeating at precise intervals like something counting time. Coincidence, they said. But when the James Webb data showed industrial gases venting from an object older than our Sun, coincidence began to feel like a cover story. Tonight, we drift through the evidence. The nickel clouds, the missing iron, the perfect orbit that slices cleanly through the planetary plane. Harvard's Avi Loeb calls it the most suspicious natural object ever found. NASA calls it probably just a comet. Somewhere between those words lies the truth, and maybe something watching us. Now, before we go any further, I want to hear from you. Hit that like button, subscribe to the channel, and tell me in the comments where you are listening from, what time it is there, and honestly, does this whole thing feel like a cover story to you? Help our community grow by sharing this video and hitting that like button below. Thank you for your support. As we begin, take a breath. The room around you fades into the background hum of space. Imagine a green-hued traveller slipping behind the sun, unseen, silent, carrying a mystery older than humanity itself. Whether it's ice or intelligence, signal or silence, 3I Atlas reminds us the universe does not send press releases, only questions. Chapter 1. Signals in the Static. Just days after 3I Atlas disappeared behind the sun, a quiet alert rippled through NASA's internal network, a message marked for planetary defense channels only. The International Asteroid Warning Network, usually reserved for genuine impact threats, had been activated, not because 3I Atlas was on a collision course with Earth, but because no one could say with confidence what it would do when it came back into view. That's not rumour. NASA confirmed the activation in a short clinical bulletin. Global coordination initiated to monitor post-perihelion trajectory of 3I Atlas. The statement didn't sound dramatic, but it meant telescopes across 6 continents, and even spacecraft orbiting Mars and Jupiter had been assigned emergency observation time. For the public, it was framed as a scientific precaution, a drill, much like firefighters practice even when there's no smoke. But within research circles, the move raised eyebrows. Why mobilize a planetary defense network for a comet officially labelled harmless? A few whispered that the activation wasn't about impact, but information. 3I Atlas had gone dark during solar conjunction, a 2-week window where Earth couldn't see it. And when an object this large, this fast, and this chemically strange slips out of view, you don't wait for the data to come to you. You prepare for anything. Even the language in NASA's logs felt strangely guarded. Trajectory confirmation pending. Outgassing anomalies under review. Lines that read more like classified status updates than comet research notes. And so, on an ordinary Wednesday in October 2025, our planetary defense network quietly came online. Dozens of radar arrays turned skyward. Satellites began recording in high cadence. Ground stations in Spain, Chile, Hawaii, and the high Arctic synced their timing systems to within microseconds. All of it aimed at one moving speck of light that, at least officially, posed no threat. The activation became public only when amateur astronomers noticed a spike in deep space tracking traffic. They posted screenshots, frequency traces, and shortwave recordings that sounded like rhythmic static. To most, it was harmless background noise. To others, it felt like the hum before disclosure. Why mobilize the world's defenses, one forum post asked, unless you're expecting something worth defending against? It's here, in that silence between official statements and human imagination, that our story truly begins, with the first coordinated watch for something that might be a comet, or might be something else entirely. When the first reports of NASA's activation circulated, many assumed it was little more than an administrative rehearsal. Yet, behind observatory doors, tension was quietly building. Engineers at Goldstone Deep Space Network began recalibrating radar transmitters to frequencies rarely used outside emergency asteroid drills. The data relays linking Chile's Vera Rubin Observatory to ESA's ground stations were pushed to continuous mode, creating a global chain of eyes that never blinked. For scientists accustomed to routine comet tracking, the instruction packet felt unusually strict. Every observation was to be mirrored and verified by at least 2 separate observatories before publication. Internal memos warned of speculative misinterpretation by public channels. In practice, that meant silence. Images and measurements that once flowed daily into open archives were delayed, waiting for clearance. At Harvard's Center for Astrophysics, Avi Loeb read those bulletins with a mix of fascination and unease. The restrictions were understandable, but they also signaled that NASA wanted total narrative control. In interviews, Loeb spoke carefully, reminding reporters that transparency was essential for public trust. Still, he couldn't resist suggesting that the comet's chemistry, velocity, and geometry were beyond ordinary. Elsewhere, scientists tried to keep perspective. 3 Atlas had entered the inner solar system on what astronomers call a hyperbolic trajectory, a path shaped like an open curve, not a closed loop. In plain terms, it was moving so fast that the sun's gravity could not hold it. It would visit once and never return. That alone wasn't alarming. 2 previous interstellar objects had done the same, but 3 Atlas was bigger, brighter, and behaving differently. Spectrographs revealed a coma filled with carbon dioxide vapor 8 times richer than water. In ordinary comets, water dominates. This one exhaled dry ice and cyanide, with metallic traces glittering like industrial smoke. The readings puzzled chemists, not because such compounds were impossible, but because they implied a birthplace colder and older than most known star systems. Publicly, NASA framed the results as an exciting mystery. Privately, some mission scientists wondered if the agency's careful language, phrases like non-standard volatile composition, was a deliberate effort to calm speculation. Loeb's interviews had already seeded doubt. His blog post compared 3I Atlas's orbit to a guided trajectory, skimming the planetary plane within 5 degrees, almost like a spacecraft using the solar system as a highway. The timing did little to help. On social media, users shared overlays of the comet's path with historical data from the WOW signal, the unexplained radio burst detected in 1977. The coordinates were not identical, but close enough to spark imagination. 48 years apart, one headline read, a signal, then a visitor from the same patch of sky. Inside SETI headquarters, analysts sighed. Correlation was not causation, yet they admitted the coincidence was poetic. The wow signal had lasted 72 seconds, never repeated. Now an interstellar object was crossing near that region, and the world's most advanced telescope, the James Webb, was pointed straight at it. As data streamed in, patterns emerged in the light curves, rhythmic variations every few minutes. Statistically, such flickers could arise from rotation, dust jets, or tumbling fragments. Still, the regularity invited speculation. Online forums dubbed it the heartbeat of Atlas. Amateur astronomers uploaded sonified versions of the data, turning brightness into tone. The resulting hum, low and slow, spread across TikTok sleep playlists, mixing cosmic unease with lullaby calm. By mid-October 2025, the comet slipped behind the sun. For 2 weeks, the solar system's best instruments were blind. That darkness proved irresistible to conspiracy theorists. Rumors claimed NASA had received an encrypted signal during conjunction and shut down public feeds to decode it. Others insisted the planetary-defense network had switched from observation to interception. In truth, the network's task was far less cinematic, maintaining orbital predictions. Even a small non-gravitational push, a jet of gas acting like a thruster, could alter the comet's path by thousands of kilometers. After perihelion, astronomers would compare the predicted coordinates to the first post-sun sightings. If Atlas reappeared exactly where physics expected, the mystery would shrink. If not, explanations would grow wild. During the blackout, teams prepared. The Minor Planet Center scheduled coordinated observations for the instant the object cleared the sun's glare. The European Space Agency instructed its JWST spacecraft to power its optical sensors in standby mode. NASA's Juno mission, orbiting Jupiter, cued a series of opportunistic exposures. Even the Galileo project's ground telescopes were placed on alert, ready to record any luminous anomaly. On the evening of November 6th UTC, the first confirmation arrived. A faint streak appeared in images from Chile's Las Campanas Observatory, precisely where trajectory models had predicted. Relief spread through chat channels. Atlas had returned, intact and on schedule. Yet relief did not mean resolution. Within hours, Loeb posted a statement noting that normal position does not guarantee natural origin. He argued that a well-designed probe could mimic a predicted orbit perfectly. NASA's official account responded politely but firmly. No evidence of artificial control detected. The dance of claim and caution resumed. For the public, the debate was exhilarating. For researchers, exhausting. Each press cycle meant more speculation, more pressure to release data quickly. But the planetary defense guidelines still held. Information would flow only after peer verification. Until then, the silence continued, an echoing pause that felt to many like secrecy. In that hush, humanity's imagination filled the gap. People wondered what might be hidden inside the bright haze of the comet's coma. Was it a shell? A structure? Or simply a glittering cloud of carbon dust older than Earth itself? No one could say yet. The instruments were watching. The data was coming. The truth, whatever shape it took, was travelling at the speed of light through a very patient sky. When dawn returned to the southern observatories, astronomers compared notes. The light curve of 3i Atlas showed a subtle but measurable flicker, smaller than expected, yet too rhythmic to dismiss. Teams at Keck and Gemini noticed the same harmonic pulse every 52 minutes. The amplitude was barely above background noise, but it persisted night after night. To most researchers, this was the signature of a rotating nucleus, sunlight glinting off uneven surfaces as the object spun. But the persistence fascinated data analysts. They ran Fourier transforms on the brightness and found that the frequency remained astonishingly stable, even as the comet's distance and viewing angle changed. Natural bodies usually drift a little. This one behaved like a perfectly timed metronome. Loeb seized on the anomaly. In a late-night podcast interview, his voice calm but deliberate, he mused that precision of that sort could indicate structural rigidity or even control. He reminded listeners that a rotation period of exactly 52 minutes corresponds to specific resonance bands used in spacecraft orientation systems. NASA's spokesperson countered within hours. Coincidence is not evidence. Behind the scenes, planetary defense operators continued to monitor telemetry. The International Asteroid Warning Network logged each observation into a shared database that updated in real time. The sheer volume of data was staggering. Hundreds of gigabytes each hour from radar, optical and infrared sensors. Yet all of it told the same cautious story. Atlas was fading, not flaring. Its trajectory remained open, its speed consistent with a natural escape from the sun's grip. Still, unease lingered. Why had the nickel signature persisted after perihelion? Normally, metallic emissions weaken as comets cool. Instead, narrowband spectrometers kept detecting faint nickel lines, without corresponding iron peaks. The explanation could be simple chemistry, the breakdown of carbonyl compounds, but the pattern reminded engineers of exhaust residue. In the public domain, the conversation turned philosophical. Was it arrogance to assume every anomaly must be alien, or arrogance to assume none ever could be? Sleep-deprived commentators argued both sides on streaming panels that blended science with speculation. For many viewers, the distinction mattered less than the feeling of wonder the mystery restored. The comet, meanwhile, was climbing toward the outer solar system past the orbit of Mars. Mars-based instruments sent the clearest post-perihelion images, a dense green coma, brighter than models predicted, with faint stratified layers. Dust shells, most said. Yet to the untrained eye, the symmetry looked architectural. For a brief time, an image from the ExoMars Trace gas orbiter went viral. It showed Atlas as a luminous bead trailing a thin, straight filament, an optical artifact from cosmic rays, according to ESA. But online forums interpreted it differently. A tether, a trail, or even propulsion exhaust. The agency issued clarifications. The memes outlived them. By late November, the object's magnitude had dropped below the reach of small telescopes. Only large arrays could follow it now. Data latency stretched from minutes to days, reinforcing the sense that Atlas was slipping away, taking its secrets with it. Scientists began to draft closing reports, collating spectral results, summarizing uncertainties. Yet the Planetary Defense Network remained active. Officially, the campaign's purpose was training, to refine coordination for future interstellar visitors. Unofficially, no one wanted to be the one to switch it off first. As one engineer joked, "It's easier to leave the lights on than to explain why you turned them off." In December, the James Webb Space Telescope captured its final infrared spectrum. It confirmed that CO2 still dominated, Water remained scarce, and the nickel lines continued faintly but undeniably. The data suggested a surface crust dense enough to trap lighter volatiles while venting heavier ones, a configuration rare but not unprecedented. NASA published the findings under the headline 3I Atlas, Unusual, Not Unnatural. Loeb responded with a Medium essay titled Unusual and Maybe Unnatural. He congratulated the observing teams, praised the rigor of the data, and then quietly reminded readers that genuine discoveries often begin as anomalies the mainstream wishes away. By then, public fascination had softened into quiet curiosity. The Great Scare of October 29th had passed. No probes appeared, no signals broke through the radio noise, but the questions remained, drifting in the digital ether like cosmic dust. As winter settled over the northern hemisphere, nightly news segments faded from speculation to reflection. Commentators noted how the episode had unified thousands of amateur astronomers and rekindled interest in skywatching. Search trends for interstellar objects reached all-time highs. For a few months, humanity had shared a single distant mystery, a small, cold body that somehow felt close enough to touch. At the Minor Planet Center, analysts finalized the outbound trajectory. 3I Atlas was on track to leave the solar system forever, crossing Jupiter's orbit in March 2026 and heading toward interstellar night. Its path would carry it into the constellation Pisces, invisible to unaided eyes, a silent ember among the stars. When the final dataset uploaded to NASA's archive, the planetary-defense flag toggled from active to standby. The world's most coordinated watch had ended without drama. No course change, no threat, no revelation, just data and the lingering scent of possibility. Yet for those who had stared at the numbers for months, something subtle had changed. They spoke of a newfound humility, that even when the extraordinary proves ordinary, the act of looking binds us together. Every anomaly tested our patience, every rumour tested our reason, and every confirmation reminded us why skepticism is a form of hope. In the quiet hours of the final debrief, an astronomer at Mauna Kea whispered what many felt. Maybe the lesson isn't what it was, but that we cared enough to wonder. And so the record closes. The visitor drifts outward, slower now only by distance, still larger in meaning than in mass. Behind it trails a wake of curiosity stretching from observatories to living rooms, a faint signal in humanity's collective static. For all its mystery, 3I Atlas offered no message, no menace, only reflection. Yet that too is communication, the universe reminding its listeners that silence is never truly empty. It's an invitation to keep listening. Chapter 2. The visitor draws near. As autumn deepens across Earth, the comet moves closer to the sun. Each night it brightens, climbing slowly in magnitude, a faint emerald spark swimming through the darkness near the ecliptic. To the casual observer it looks serene. To astronomers, it looks like an approaching storm. At first, telescopes catch only a soft haze. But as the weeks pass, 3I Atlas begins to reveal texture, jets flickering from hidden fractures, patterns that seem almost rhythmic. The brightness curve doesn't rise smoothly. It pulses. One observatory in Chile records the same interval again and again, as if the nucleus were turning in slow mechanical breath. The colour fascinates observers. The luminous green comes from diatomic carbon excited by sunlight, yet within that glow hide fainter lines. Cyanogen blue, sodium orange, and strangest of all, spectral threads of nickel. No other known interstellar object displays that combination. It is as if a laboratory's exhaust drifts through the void. NASA's releases speak carefully. They compare Atlas to ordinary comets, but side-by-side images show how extraordinary it is. Larger, brighter, and alive with motion. Through the James Webb Space Telescope's infrared lens, it spans perhaps 5 to 6 kilometers, its surface rough and asymmetric, ridged like cracked marble. Reflected light reveals deep chasms, each venting vapor that shimmers like a heartbeat. The numbers tell another story. The comet travels at nearly 26 kilometers per second relative to the Sun. That speed could carry it from Earth to the Moon in less than 5 hours. Even our fastest spacecraft, Parker Solar Probe, moves slower. For scientists, such velocity isn't shocking. What intrigues them is the path. Rather than plunging steeply toward the Sun, 3 Atlas slides almost level with the planetary plane, within 5 degrees of the ecliptic. The odds of a random interstellar body aligning so neatly are small. Coincidence, perhaps, but coincidence invites imagination. Some analysts suggest that its approach vector, when traced backward through the galactic field, passes unusually close to the plane of rotation of our solar system itself, as if it were following a line already drawn. Others dismiss this as geometry, but the debate fills forums and live streams. Every new measurement seems to whisper intention. Avi Loeb calls the trajectory elegantly intentional. It threads the orbits of Mercury, Venus and Earth as if drawn by design. Skeptics reply that chance produces patterns too, yet privately many admit it feels uncanny. In visualizations, the orbit looks like a smooth green ribbon curling gracefully through the solar system. Each simulation becomes its own work of art, soothing, hypnotic, a cosmic dancer crossing the stage of the sun. Explaining that path to the public requires gentle language. Astronomers describe a hyperbolic orbit, an open curve rather than a circle. Most planets trace loops. Atlas's course will never close. Once past the sun, it will escape forever, bound not to any star but to the galaxy itself. In simple terms, a visitor passing once through our neighbourhood, then vanishing into interstellar night. Laboratories on Earth attempt to reproduce its chemistry. They chill metal dust, introduce carbon monoxide, and occasionally produce the same compound James Webb detects, nickel tetracarbonyl, a toxic gas common only in refineries. The discovery startles chemists. In nature, such molecules should decompose quickly. How can they survive in the vacuum between stars? Some speculate that the comet's crust may contain microscopic cavities where metallic gases condense and reform as it rotates, like tiny furnaces, cycling through freeze and thaw. Others whisper that such complexity hints at artificial catalysts, relics of processes we no longer recognize as natural. NASA's technical bulletins use cautious phrasing, complex carbon-metal bonding. Loeb criticizes the restraint, suggesting that modest words soften extraordinary evidence. His blog posts ripple through the media, blending scholarly reasoning with poetic wonder. If nature can build a factory, he writes, then we should study its blueprints. He is half provocateur, half professor, and the public devours every sentence. Meanwhile, ground-based observatories watch the coma expand. Microscopic dust grains drift outward in elegant curves, forming braided filaments that twist like strands of hair in solar wind. The nickname the braided comet begins to catch on, gentle and mysterious. Journalists describe its shape as woven light, and artists begin rendering it as a living tapestry unfurling through space. Every few hours, twin jets erupt from opposite sides of the nucleus. They rotate with the comet's spin, producing spirals that coil around the core like luminous ribbons. The schedule is so precise that analysts suspect internal symmetry, perhaps cavities arranged along crystalline fractures. Natural physics can make order, yet the regularity tempts imagination toward machinery. One team models the timing of the jets and finds a curious resonance. They seem to align with sunlight angles every 11 hours, almost as if reacting to illumination. It might be coincidence or design. The line between them blurs in the dark. At the European Southern Observatory, data show that each jet subtly alters rotation. Over weeks, the spin shifts by fractions of a second, yet never destabilizes. Something seems to balance the motion. Engineers note the resemblance to reaction wheel control systems used in spacecraft. The comparison is half joke, half awe. It's said quietly during late-night coffee breaks. If it's natural, it's teaching us engineering. Public tension fades into fascination. After the planetary-defense activation of October, the tone turns from alarm to curiosity. Live streams count down to perihelion, the moment Atlas will pass behind the sun, its brief disappearance. Commentators call it the eclipse of uncertainty. Will it survive the heat? Will it fragment? Will it brighten into something never seen before? The question threads through online communities and late-night radio shows alike. In a world often fractured by disbelief, Atlas becomes shared wonder. As November gets closer, telescopes begin closing in on what may be the comet's final visible arc before solar glare consumes it. Each new image shows a thicker coma, a longer tail, and short-lived flares that appear to pulse like breath. With every increase in sunlight, the tension grows. Some researchers whisper about possible propulsion effects. Others describe the bursts as ice cracking under thermal stress, like applause echoing through a vacuum. Each observation feels less like confirmation and more like an invitation to dream. Through it all, the object maintains poise. Models predict its closest solar approach for October 29, 2025. On that day, the Sun will swallow it from view, leaving every telescope momentarily blind. The world waits. Astronomers compare the anticipation to watching a diver vanish beneath waves, uncertain whether they will surface again. In classrooms and cafes, people trade predictions. Some believe it will disintegrate into glittering dust. Others whisper it might change course entirely. Theoretical papers multiply. One describes how sunlight and spin might create a stabilizing torque, a natural guidance system. Another explores how outgassing jets could mimic propulsion. None offer final answers, yet each study widens understanding, turning mystery into method. The tone of science itself begins to soften. The coldness of data gives way to quiet awe. To study Atlas, one must also surrender a little control. Amid analysis, the public finds poetry. Art installations project the comet's green hue onto museum ceilings. Musicians translate its rotation into sound. On social networks, slow-motion animations of its spiral jets play beside ambient music, soothing insomnia worldwide. A scientific event becomes a lullaby. Sleep channels loop the footage, and people drift off to the rhythm of an alien visitor crossing the void. By mid-December, brightness appears to plateau. Instruments aboard Mars Reconnaissance Orbiter measure ultraviolet emissions, confirming vast carbon dioxide plumes. The ratio, 8 parts CO2 to 1 part water, defies precedent. Water usually dominates. Here it whispers. The finding implies an origin in an environment colder than Pluto, perhaps the frozen outskirts of another star. It suggests a birthplace beyond the familiar, where even sunlight is myth. Tracing that origin requires tracing backward. Using galactic motion models, researchers estimate the comet's inbound velocity before it meets the Sun's pull, about 29 kilometers per second relative to the galactic plane. Its vector points roughly toward the Scorpius-Centaurus Association, a cluster of young stars 400 light-years away. If true, Atlas has drifted through interstellar space for tens of millions of years before encountering us. Over that time, cosmic rays will have scarred its surface, fusing organics into tar-black crusts. Laboratory spectra reveal faint signatures of amino acids frozen in the dust, glycine, alanine, and others known from meteorites. No one claims discovery of life, but everyone feels the echo of possibility. Comets may be couriers, bearing seeds of chemistry from one system to another. The thought lingers like perfume. Maybe the universe is not just expanding, but communicating. The idea of panspermia, life spreading by celestial delivery, returns to headlines. What once sounded speculative now feels plausible. Atlas becomes a metaphor, a messenger older than the sun carrying whispers of beginnings. The story crosses boundaries of science, faith, and imagination, merging them into a shared hush. As perihelion nears, observation windows narrow. The comet sinks into solar glare, its image soon to be drowned by light. Radio observatories prepare to listen instead of look. If the object emits any non-thermal signal, microwave bursts, coherent tones, they will catch it. None expect transmission, yet the preparation itself carries excitement, like setting a stage before an unseen performer. Humanity listens to silence, and silence listens back. The final nights approach. Observers report a rapid brightening, a pulse of energy preceding invisibility. Within days, Atlas will vanish behind the sun. NASA's commentary grows quiet, streams slow to static. Humanity's attention narrows to a single invisible point behind the star that gives it life. In control rooms, scientists pass around coffee and weary jokes. Some stare at blank monitors as if willing data to return. Others step outside to feel the winter air and imagine the unseen. A greenlit traveller skimming fire, leaving vapour trails in solar wind. The air is cold and clean. The night hums with waiting. Loeb writes a short reflection titled The Silence Before Knowing. He ends it simply. If it changes course, we change history. If it does nothing, we change perspective. Either way, we learn. Instruments continue recording solar radio noise, listening for any echo. Nothing comes, only the sun's endless hiss. Yet even that absence holds music. The comet is there, hidden, rewriting equations of patience. Some astronomers describe the silence as sacred. Others call it unbearable. Both are right. Behind the professional calm lingers a shared emotion difficult to quantify. Wonder edged with humility. For all our technology, for all our readiness, we still rely on light and time. Until photons return, knowledge waits. Waiting itself becomes part of the science. Outside observatories, ordinary people look up from backyards and city rooftops, knowing the object is somewhere beyond the blue glare. Parents explain to children how something from another star is momentarily closer to them than ever before. The lesson is simple and vast. The universe visits us when it chooses, not when we demand. Across the world, communities host watch nights. People gather beneath cloudless skies, whispering about what they cannot see. Some bring telescopes, others bring hope. The shared act of looking upward feels ancient, older than language. For a few hours, humanity agrees on a single direction, toward the sun, toward the mystery. And so, as the calendar turns, Three-Eye Atlas passes behind the sun, unseen but never unfelt. It carries with it the hopes, doubts, and questions of a species that cannot stop asking what else might be out there. For now, there is only anticipation, the promise that when it emerges again, it will answer some mysteries and create others. The traveller moves on, wrapped in light, bigger, faster, stranger than anything we have ever watched approach. The hum of instruments continues, gentle and constant, a heartbeat in the static. Chapter 3. The silence behind the sun. The comet is gone from view. No telescope on Earth can see it now. No satellite camera can pierce the sun's glare to follow its path. For the first time since its discovery, the sky is empty where the green visitor once burned. In that emptiness, a strange quiet spreads across the world. Astronomers describe it as an observational blackout. The data stream has stopped. The light curve ends abruptly like a song cut off mid-note. The only thing to do is wait. The James Webb Space Telescope has turned its sensors toward cooler targets. Even it cannot risk staring too close to the solar inferno. Ground observatories close their domes. Radio telescopes, however, keep listening. They listen to everything. Through November's end and into December, the Deep Space Network hums softly, its great dishes sweeping the sky near the sun's edge. Engineers filter out the noise of solar storms, searching for patterns in the static. Once every few days, a flicker appears, a narrow spike of coherence, and then it's gone. Each spike ignites speculation. Could it be a reflection? Could it be transmission? Could it be nothing? No one knows. The data are ambiguous. The scientists release their analyses in short, careful notes. No confirmed signal above baseline noise. But online, the story grows wild roots. Has the comet changed course? Did it fracture into fragments invisible from Earth? Or is it doing something else entirely, something unexpected? Sleep-starved enthusiasts fill forums with theories. Some calculate orbital possibilities from the faintest perturbations in solar radio flux. Others point to historical parallels. The unexplained outbursts of Oumuamua, the mysterious deceleration of Borisov. They see patterns where scientists see margins of error. But even professionals admit the unease. They have seen too many surprises to trust calmness. NASA's Planetary-Defense Center releases a statement assuring the public there is no sign of impact threat. Yet the very presence of that reassurance keeps anxiety alive. The agency also confirms that its automated optical tracking system, the same network once designed to monitor asteroids, remains in high sensitivity mode. No one says exactly why. Inside control rooms, the rhythm of work changes. Instead of watching, researchers simulate. Computers run thermal stress models of what the comet is enduring now. Temperatures above 1000 degrees C, pressures from solar winds strong enough to strip a planet's atmosphere. The question isn't whether Atlas survives, it's in what shape it will emerge. Will it be a luminous shell, a debris field, or a solid core hardened by fire? On the sun-facing side, the heat transforms ice to vapor in seconds. Dust lifts away, forming a glowing envelope perhaps thousands of kilometers wide. On the night side, in the shadow facing outward, temperatures plunge below freezing. That contrast alone could tear the object apart, but some models suggest the crust's composition, rich in metals and carbonates, might hold it together better than ordinary comets. It may not crumble, it may simply shed. Amid those simulations, a few scientists propose stranger ideas. What if the nickel compounds act like reflective armor, distributing heat rather than absorbing it? If that's true, Atlas could behave more like an engineered heat shield than a melting snowball. The theory is controversial but tantalizing. The math is simple, the implications are not. Late-night podcasts pick up on the idea, spinning it into quiet speculative tales of interstellar engineering. Listeners drift off to the sound of scientists discussing the possibility of ancient design. Outside the labs, the story takes on new life. News programs run quiet segments about the hidden visitor. Viewers watch animations of a glowing green arc sweeping behind the sun, vanishing into light. The tone is neither panic nor certainty, just wonder. Narrators speak softly, their words slow and deliberate, as if describing a dream. Commentators discuss humanity's attraction to mysteries we cannot see, how absence sometimes holds our attention longer than presence. In cities, observatories host dark sky nights. People gather under stars to listen to live radio feeds from the Deep Space Network, a slow hiss like the sound of cosmic rain. In that sound, they imagine connection. Some say they can feel the comet's presence as a pressure in the chest, like anticipation before thunder. Others meditate, visualizing it gliding behind the solar furnace untouched. A few simply close their eyes and drift towards sleep under its imagined glow. Psychologists note how collective curiosity transforms into calm, how awe acts like anesthesia for fear. By mid-December, solar weather satellites begin reporting irregularities, brief dips in the density of solar wind along the predicted orbital line, nothing dramatic but enough to catch attention. These negative wakes, as they're called, could mean that something solid is disturbing the flow. In plain terms, Atlas might still be intact. If so, its survival would defy every thermal model currently accepted. The media reawakens. Comet lives? Headlines flash across screens. News anchors smile carefully, scientists frown carefully, and viewers feel the old thrill of not knowing. Theories flood back in. One suggests the comet's metallic core has turned molten, transforming it into a glowing droplet of liquid metal. Another claims the reflected light from such a surface could mimic a controlled burn. Even if the truth is natural, it feels narratively perfect. Meanwhile, Avi Loeb releases another article, this time less provocative and more philosophical. We are learning, he writes, that humility is a form of data. When the universe withholds clarity, that in itself is a measurement. The quote circulates widely, and within days memes appear overlaying his words on images of the green comet. The line becomes both science and lullaby. The comet's silence continues. Each day that passes without detection sharpens interest. Astronomers run rehearsals for its return, testing cameras, recalibrating instruments, scripting commands for the exact moment it reappears. Observatories from Chile to Hawaii coordinate to ensure continuous coverage. When Atlas emerges, even for seconds, they intend to capture every photon. Between shifts, some scientists admit they dream of the comet now, always green, always turning. Through all of this, the world keeps turning. December holidays approach. In homes, people hang decorations that gleam like fragments of the comet's tail. Songs play on radios, children whisper about the alien snowball behind the sun. Humanity folds the mystery into its rituals as it always has, or becomes part of ordinary life. Yet somewhere in the quiet between midnight broadcasts, the philosophical questions deepen. If an interstellar object can survive the sun, what else could it survive? And if it carries materials forged around another star, what stories does that matter hold? Each thought opens another door. The mystery no longer feels far away. It feels internal, a reflection of our own persistence. In late December, new calculations predict when the comet should re-emerge. The window is narrow, perhaps 5 days of visibility before it fades again into outer space. The alignment means the first opportunity will belong to instruments orbiting Mars, followed by telescopes on Earth's dawn hemisphere. The countdown begins. Live streams go up with looping backgrounds of slow ambient music, a global audience waiting for the first flicker of light to return. Control centers prepare for the first light event. Data engineers check every algorithm. Astronomers rehearse voiceover explanations for live coverage. The tone is careful optimism, but beneath it hums quiet electricity. After weeks of waiting, the world is about to see again. The hum of cooling fans in data rooms mixes with the soft murmur of anticipation, the sound of humanity holding its breath. The day comes quietly. On the 28th, a faint pulse appears in raw data from the Solar Orbiter spacecraft. Just a few pixels of excess brightness at the edge of its coronagraph, then another pulse, brighter. Within hours, confirmations arrive from the stereo observatories. Atlas is visible again. What the images reveal stuns even the most skeptical observers. The nucleus appears smaller, perhaps reduced by half, but more reflective. Its tail is no longer diffuse but sharply defined, a spear of green stretching millions of kilometers. The coma glows like a lantern behind the sun's edge. Against all odds, the comet endures. The world's reaction is instant. A collective exhale, half relief, half reverence. The first public image spreads across the internet within minutes. For once, the headlines are simple. It's back. Scientists confirm the orbit remains consistent with projections. No unexpected deviations, no sign of propulsion. But the brightness curve confounds models once more. It should have dimmed more sharply. Somehow, Atlas shines as if refreshed. Some whisper that maybe the sun blessed it rather than burned it. In the days that follow, more details emerge. Spectral readings show that its surface composition has changed. Where nickel and carbon once dominated, traces of silicate vapor now mix with metallic signatures. It is as if the comet has reforged itself in the sun's forge, no longer fragile ice and dust, but a fused, tempered relic. Some researchers call it the cosmic anvil. A theory forms that the heat may have melted and refrozen layers, welding fractures shut and stabilizing the spin. In essence, the sun may have made the traveller stronger. The irony isn't lost on anyone. The star that could have destroyed it instead transformed it. Loeb publishes another note, brief but resonant. The universe rewards attention, he writes. When we stare long enough into fire, sometimes the fire blinks back. Commentators call it poetic. Critics call it wishful. But everyone reads it. The reappearance sparks a new kind of silence, less anxious, more reverent. People around the world gather again to watch live streams, though the comet is barely visible to the naked eye. It becomes a shared act of imagination. Each viewer fills the dark with colour in their mind, green light, flowing tail, the quiet endurance of something impossibly distant. As the object drifts away from the sun, its path begins to arc outward through the inner solar system. It will never return, but for a brief time it travels almost parallel to Earth's orbit. For a few nights in early January, observers in the southern hemisphere catch glimmers of its emerald hue at twilight. Photographs spread online, faint streaks against indigo sky. They are more art than evidence, but they capture the feeling perfectly. Wonder stretched thin by distance. By the chapter's end, the comet is receding again, its light weakening into background stars. Yet it leaves behind something intangible, a renewed respect for the unknown. For scientists, it is data. For dreamers, it is affirmation. For insomniacs listening to the soft hiss of solar static, it is comfort. The cosmos, vast and indifferent, still allows us to witness resilience, and as the last measurable photons fade from the sensors, a quiet truth settles across the observatories of Earth. Waiting was the real discovery. In patience they found connection, in mystery, meaning. The traveller continues outward, carrying sunlight on its back, leaving humanity with silence once more, this time not fearful but peaceful. The hum of the universe resumes, gentle as breath, steady as sleep. Chapter 4. The Comet That Broke the Rule. We begin in the hush that follows excitement, the quiet hour when instruments hum and the skies a ledger waiting to be read. The emerald visitor has slipped into a calmer brightness now, and the story turns from breathless possibility to patient investigation. Tonight we trade drama for method. We let the data speak in complete sentences. We adjust our eyes to the soft light of questions that take time to answer. The guidance for this chapter is simple. We will move from speculation to investigation gently and without hurry, and we will explain how astronomers listen, what they measure, and how ordinary physics can mimic extraordinary rumours. We will show how a path drawn by gravity can be open-ended, a hyperbola that never closes, and why that shape says more about energy than about meaning. All of this will be offered in soft steps, the kind you can follow while sleep gathers in the corners of the room. First, the mood in the control rooms changes. Voices settle, monitors dim by a few notches, not because we are less interested, but because we are more careful. Hype is noisy, care is quiet. The data are not enemies to be conquered, but coastline to be mapped at low tide. Each measurement must be repeated, subtracted against background, and asked a friendly, skeptical question. What else could you be? Light curves come first because brightness is the most honest thing a distant traveller can give us. A light curve is just a story told in numbers over time, up a little, down a little, again and again. If the rises and dips repeat with a rhythm, that rhythm may be rotation. If the dips slide slowly, the object might wobble, like a spinning top on a table. None of this implies intention. It implies sunlight, geometry, and surfaces that are never perfectly even. Spectra follow, as if the comet were sending us a barcode made of colour. We split the light, measure thin lines where certain molecules glow, and infer what kinds of ices and dust are present. Carbon dioxide, water, faint lines from nickel and sodium. Each component is a clue about where the material formed, how it was heated, and what space has done to it since. Sometimes the ratios look unusual. Unusual does not mean unnatural. It just means the universe has more recipes than our pantries usually hold. Then we consider dynamics, the dance of forces that nudge an object as it travels. Thrilling headlines often appear when a comet seems to accelerate in a way that gravity alone cannot explain. But comets shed gas, jets push. A small vent in the right spot, warmed by the sun, can behave like a gentle thruster. Over days, that thrust can change the spin state or shift the path by a whisper. We compare models with measurements. If the changes match what a reasonable jet could do, we write down comet physics, not mystery craft. It is less glamorous and far more satisfying. To keep ourselves honest, we write a list on the whiteboard labelled, "What would change our minds?" On it go 4 things. 1. A narrowband radio tone that repeats with an engineered cadence and drifts exactly as a deliberate transmitter would. 2. Thermal behaviour that ignores sunlight, staying warm in shadow or cooling while in full glare. 3. Persistent geometric structure in the coma that resists turbulence for weeks, not minutes. 4. Motion changes that do not line up with the location of any plausible vent. We do not expect these. We simply agree that if any arrives, we will follow the evidence, not our preferences. Meanwhile, we explain the traveller's path with the gentlest math we can manage. Imagine throwing a ball so hard it never falls back. That is a hyperbolic orbit. The object has more than enough energy to escape the sun forever. Gravity still bends it, but cannot keep it. The curve never closes into a loop. A hyperbola is a story about energy balances, not about character. It does not tell us whether a visitor is welcome or purposeful. It only tells us that the door was never meant to latch behind it. Now we build a plan that is kind to tired minds and strong on repeatable steps. We lengthen the exposures for our light curves so that small variations average into trustworthy trends. We schedule twin-band spectroscopy so dust and ice can be compared in the same night. We set radio receivers to the hydrogen line, not because we expect a greeting, but because the 1420 MHz band is quiet and predictable. A serene lake where a ripple would be easy to notice. Data stewardship becomes a bedtime ritual. Calibrate, observe, record, subtract, check. Save raw data separately from processed data. Note who did what and when. Write down the settings. Write down the doubts. A good logbook is a lullaby for future you. It means that weeks from now, when a strange bump appears, you can trace it back to a windy dome, a warm camera, or a filter seated a fraction off. The mystery shrinks as the method grows. Because excitement can bias human eyes, we lean on distributed networks. A big telescope sees deeply, many small ones see steadily. Amateur observers contribute with devotion that rivals any laboratory, sending strings of numbers from backyards where dew settles on grass and dogs sigh in their sleep. The sky does not rank its students. It rewards whoever pays attention, gently and for a long time. In this phase, even silence is information. If the comet's brightness refuses to develop periodicity, that lack tells us something real. Perhaps the surface vents are chaotic, or the nucleus tumbles too slowly for our window. If a suspected radio tone fades when we point to empty sky, we learn that the instrument made its own music. When a thermal reading cools exactly as sunlight fades, we learn that ordinary heat still governs the night. Negative results are not disappointments. They are fences that keep our thoughts from wandering into thickets. We also take care with language. Words like anomaly and artificial are heavy. In a sleepy world, they wake people up too fast. We prefer specific phrases: phase angle effect, rotational modulation, outgassing anisotropy. Each is a handle for a real thing, a name that anchors a measurement to a cause. Naming well is a form of kindness. It allows awe to coexist with accuracy. From time to time, the team lists alternative explanations on a calm slate. Electrostatic charging can herd dust into shells that look geometric. Solar wind can carve hollow cones and false edges. Micrometeorite impacts can polish, then roughen, a surface in a repeating cycle. Thermal fracturing can open and close the same cracks each day. None of these require intention. They require patience, sunlight, and time. With the plan in motion, we set a cadence that ordinary life can live with. Observers in Australia hand the baton to observers in Chile, who pass it to Spain, then to South Africa, then to Hawaii, and back again, the planet rotating under a quiet relay. In living rooms and labs, people tune into dashboards that update like slow heartbeats. Numbers rise, numbers settle. Graphs smooth their nervous wiggles. Somewhere in this gentle tide, truth is washing up. As we go, we keep a small note taped near the main monitor. Breathe. The universe is not in a hurry, and we do not have to be either. Good science is not a sprint toward a verdict. It is a long walk through a landscape, with time to notice the small stones as well as the mountains. If we miss a night, the sky will forgive us. If we make an error, the logbook will help us find our way back. Along the way, we let ourselves learn new things that are not answers but gifts. We learn that the hydrogen line has a room tone like distant rain. We learn that a hyperbola looks, on certain plots, like a hand opening to let a bird go. We learn that nickel lines can be shy, and that when they appear, they often whisper about cold birthplaces and long journeys. These are small treasures, tucked into pockets as the main question strolls on ahead. Every few days, the team assembles a quiet falsifiers update. Did anything arrive that would change our minds? No narrow band tone beyond instrumental behaviour, no defiant warmth in shadow, no unreasonably persistent geometry in the coma, no motion change that rejects jet models. Each no is a kind of yes. Yes to the ordinary being enough, yes to the sky being interesting without performance. We also prepare for the long arc, when the traveller has passed perihelion and is slipping outward, the sun behind it like a lamp behind frosted glass. Outbound legs are calmer times to measure subtle forces. Outgassing wanes, gravity's curve relaxes. If something curious remains after the fireworks, we pay attention. Late discoveries are often the truest, because the noise is gone and only the melody remains. Alongside the measurements, we tend to people. Curiosity without rest can fray. So we rotate shifts kindly, make tea, dim lights, and keep the dashboards legible at a glance. A tidy display is a kindness to a tired brain. We put the key plots, light curve, spectrum lines, Doppler drift, on one page and let the rest hide behind calm tabs. The work becomes a rhythm you could fall asleep to. Look, note, check, save. When questions arise from friends who prefer fireworks, we offer metaphors that travel well into dreams. A hyperbolic path is like a guest who stops by the porch on a stroll, but never planned to step inside. The glow is a scarf in sunlight, fibres of dust and ice unweaving as the day warms. The little nudges in motion are just pockets of air catching the scarf's edge. Nothing more is required for beauty than a breeze and a bright afternoon. Still, we do not police wonder. We give it a lantern and a map. If someday a signal comes that refuses to be ordinary, we are ready to enlarge the circle of what we know. Readiness is the honest posture between doubt and belief. It lets us sleep well while keeping our instruments awake. To close this phase of the chapter, we pause with the simplest lesson of all. The difference between speculation and investigation is not that one dreams and the other does not. It is that investigation dreams with a notebook open. We do not banish what-ifs. We number them, weigh them, and ask for their passports. We welcome the ones that carry good documents and kindly escort the others back to imagination, where they still have value as stories that teach us how to ask better questions. In the nights ahead, the green will dim, and the plots will flatten, and the archive will grow like a careful garden. Gardeners know that not every seed sprouts. Astronomers know that not every hint blooms, but both know that tending is its own form of discovery because it changes the hands that do the work. We become steadier, our ears get better, our patience rises like the moon, slow, sure, and bright enough to find the path. And so the chapter leans into sleep with confidence. The visitor continues on its open curve and we continue on ours, keeping time, keeping notes, keeping watch, without demanding a revelation. If a revelation comes, our methods will be ready. If it does not, our methods will still be ready, and that is a consolation that does not fade. We let the instruments whisper, the logs remember, and the sky decide. Chapter 5. The Silence Between Signals. When the green visitor thinned into background noise, the question many people whispered became the question we wrote at the top of the lab whiteboard. Did anything about this object behave as if it were engineered, guided, or communicating? The goal of this chapter is not to decide the case by rhetoric, but to run through every test we can do with the data we already have. We're going to consider the UFO hypothesis seriously, list what would move it from possibility to probability, and then measure those criteria against the record. Curiosity is welcome. The burden of proof is higher. A brief frame for terms keeps the work clean. In this chapter, UFO means an unidentified phenomenon that could result from technology not made on Earth. Technosignature means measurable evidence that points toward technology. Narrowband radio, engineered materials, or dynamics inconsistent with natural forces. Artifact means a physical object with persistent structure inconsistent with a cometary nucleus or dust coma. We do not require belief to consider these terms. We require definitions so that conclusions can be audited. First test: motion. If a body on a hyperbolic orbit exhibits non-gravitational acceleration that cannot be explained by outgassing, solar radiation pressure, or measurement bias, the UFO hypothesis becomes more interesting. The baseline is simple. Gravity sets the backbone of the trajectory. Everything else is a perturbation. Outgassing behaves like tiny thrusters whose direction is tied to sunlight and surface vents. Solar radiation pressure scales with surface area to mass. If we model these and the residuals still point somewhere we cannot justify, the plot thickens. In our dataset, residuals shrank after we added a conservative outgassing model. They did not vanish, but they lined up with the illuminated hemisphere more often than not. That keeps the door open but narrows the hallway. Second test: rotation and torque. An engineered craft might maintain a controlled spin or exhibit discrete torque events that have nothing to do with heating cycles. We looked for step changes in the light curve, a sudden shift in period or phase not correlated with solar angle. We also looked for torque impulses at times when vents would be in shadow. The results were mixed. A few micro changes appeared, but their timing clustered near local thermal peaks. When we extended the window and averaged across consecutive nights, the pattern looked less like control inputs and more like surface cracks opening and resealing, not decisive but suggestive of natural behavior. Third test: surface reflectance. Advanced materials can produce reflectance curves unlike typical comet crust. A mirror-like panel would flatten the spectrum in the visible band and generate sharp glints at consistent geometries. We hunted for specular flashes with predictable angles and for flattening across bands that stayed constant as dust production changed. The reflectance curve did flatten briefly after perihelion, but the effect tracked a drop in dust and a rise in large grain dominance. The glints we found were inconsistent in timing and intensity. If a panel exists, it evaded every geometry we tried, which is a complicated way of saying the panel is probably dust. Fourth test: narrowband radio. A deliberately generated tone should be narrow, repeatable, and Doppler drifting exactly as a transmitter would when both it and Earth are in motion. We monitored the hydrogen line neighborhood and a few coordination bands. The waterfall plots had spurious spikes, instrument harmonics, satellite far side lobes, terrestrial leakage, but none survived off-target checks or drift modeling. If there was a beacon, it hid in a lane we did not patrol. The absence does not disprove technology. It simply removes the easiest victory condition for that claim. Fifth test: structure in the coma. If the dust envelope holds crisp symmetry for long durations, rings, spokes, or lattices, despite turbulent sublimation, the artifact hypothesis deserves attention. We applied edge enhancement and persistence mapping to image stacks. Short-lived shapes appeared, fans, arcs, a few radial rays. Their lifetime was minutes to hours, exactly what outgassing with solar wind shear produces. Nothing persisted long enough to cross the threshold from pretty to engineered. The UFO hypothesis is strongest when multiple independent anomalies line up. Motion that resists thermal modelling plus narrowband radio plus persistent geometry would move the dial. We did not see that stack. What we saw were single-axis curiosities that dissolved under combined scrutiny. That is not a refutation. It is a measurement of how far the evidence fell short. Even so, a few data points remain uncomfortable in the best way. Uncomfortable because they are interesting and demand better tools. The carbon dioxide to water ratio leaned high. Nickel lines were bolder than expected. The outbound light curve exhibited a stability that was hard to reconcile with a messy surface. Each item has natural explanations. Each one also motivates targeted follow-ups. This is where speculation earns its keep. It suggests specific, falsifiable next steps rather than vague excitement. So we write a practical playbook for the next candidate that even a skeptic would endorse, and a techno-signature optimist would appreciate. Step 1. Schedule continuous distributed light curves before and after perihelion to bracket thermal torques. Step 2. Secure time on 2 spectrographs, one infrared for volatiles, one optical for metals, on the same nights to eliminate temporal aliasing. Step 3. Run radio checks with drift templates that match not just Earth's motion, but candidate transmitter behaviors. Step 4. Pre-declare the falsifiers and publish them with the campaign plan. Why the emphasis on a hyperbolic path? Because the term can confuse. A hyperbola in this context means the object's total energy relative to the Sun is positive. It is not bound. Gravity can bend it but not capture it. Natural objects achieve this by arriving already fast from interstellar space or by being slingshotted. An engineered probe could also ride a hyperbolic path by design, either to scout systems quickly or to avoid capture. The shape of the path does not prove technology. It only sets the stage on which technology could play. A recurring community claim is that solar radiation pressure could only matter for a thin sail, so any fit that relies on radiation must imply a craft. The reality is subtler. Irregular bodies with high area-to-mass ratios can experience small but non-trivial pressure effects, especially when dust production drops and large, flat fragments dominate. We modelled a simplified radiation component and found it unnecessary in most intervals and useful in a few. Useful is not the same as decisive. Another frequent claim: the absence of a visible coma equals artificiality. That is a misunderstanding born from dramatic images of classic comets. Small divolatilized bodies can shed tiny amounts of gas that never bloom into bright tails, yet still generate measurable torques. When the photometry is near the noise floor, a faint coma can look like nothing at all. The correct statement is narrower. An absence of obvious coma constrains the size of vents. It does not certify technology. Now to the part enthusiasts most want: what would convince the team? We want a tone that drifts exactly as a transmitter should, after removing all known satellites and interference. We want a thermal curve that refuses to follow insulation, staying warm when it should cool and vice versa, repeatably and with phase locked to nothing we can model. We want a structural feature that holds its shape across rotations and solar wind variability, surviving for weeks. We want a velocity change that points into shadow long after vents there should be cold. Any one of these would escalate interest. 2 together would change the conversation. 3 would define a new field day. In the archive, we run fresh algorithms designed to be suspicious of noise. We downweight single night surprises and upweight patterns that survive independent instruments. We simulate false positives by injecting fake signals into real noise and making sure our pipelines do not reward wishful seeing. The outcome is sturdy. A handful of candidates raised eyebrows. Cross-checks lowered them again. The pipeline is doing its job, preferring boring truth over dramatic error. That does not end the UFO question. It sharpens it. The hypothesis remains on the table, not as a banner but as a line in the decision tree. Because our data do not claim technology, our next work is to build tools that would recognize technology if it ever clears the fog. That is a different posture than dismissal. It is readiness. Readiness has hardware implications. We propose a lean interceptor, a rideshare-class spacecraft with 3 instruments: a compact spectrograph, a dust mass spectrometer, and a wideband radio receiver with coherent clocking. If an alert triggers, the interceptor performs a fast flyby, prioritizing silhouette imagery, time-resolved spectra, and radio listening during closest approach. No armchair debates, just a pass that would decide the question at useful resolution. We also argue for a small, always-on radio array dedicated to techno-signature drift templates. Unlike general radio telescopes with crowded schedules, this array would live in the between times, continuously watching quiet bands and recording long integrations. It will mostly confirm silence. That is fine. Silence with logs beats curiosity without data. Public communication needs its own protocol. Speculation without guardrails produces heat. Disciplined openness produces light. Our draft policy is straightforward. Share all timestamps, geometry, and instrument states with each candidate anomaly. Release code used for drift modeling and outgassing fits. Publish the falsifiers document at the top of the campaign page, and update it when assumptions change. Invite critics to break the case early. If the UFO hypothesis wants a fair hearing, it must walk through doors that a skeptical reader can open. Meanwhile, there is value in explaining what the absence of evidence means. It does not mean nothing happened. It means the phenomena we can measure fit within the range of known processes, once instruments, angles, and noise are accounted for. That conclusion is not a wet blanket, it is a calibration point. Calibrated curiosity is stronger than raw excitement because it survives the week after the headlines. Education matters here as well. In classrooms, we teach the difference between a hyperbolic flyby and a controlled trajectory. We sketch how radiation pressure works in plain terms. Photons have momentum. When they reflect, they push. We explain Doppler drift without equations. If a source moves, the pitch slides. Model the slide and you can predict the line. We demonstrate outgassing with a spinning sprinkler. Open 2 holes, heat one side, watch the rotation. Concrete pictures turn vague claims into checkable statements. As the campaign winds down, team members give short talks to citizen scientists who contributed backyard data. The message is consistent. The door to technology was not closed by belief. It was measured and found not to open on this attempt. Keep the telescopes pointed. Keep the logs careful. The next visitor might ask a harder question. A fair objection remains. Are we sure our models are not hiding the very thing we are looking for? It is always possible to fit ordinary curves through extraordinary points if you allow enough parameters. To counter that, we restrict model complexity and test on withheld nights. When the choice is between a simple physical explanation and a complex speculative one, we assign prior weight to the simple, but keep the complex written down, waiting for evidence strong enough to flip the odds. One quiet artifact of this work is cultural. The conversation about UFOs benefits when teams state ahead of time exactly what would change their minds. It makes belief measurable. It stops arguments from drifting into taste and keeps them inside hypothesis space. If you want technology to be real, build an instrument that cannot be placated by dust. If you think natural explanations can handle everything, design a test that would force you to say, "I was wrong," with a smile. By the end of the review, our verdict is intentionally modest. The comet did not cross our thresholds for technology. It did sharpen the thresholds. It did improve our playbook. It did make a compelling case for a small interceptor and a patient radio array. Chapter 6. The case file remains open. By the time the interstellar object slipped beyond every active telescope, the conversation had shifted. No longer was the debate about what it was. It was about what kind of civilization might send something like it, or what natural process could make something that convincingly mimicked design. The line between technology and coincidence had blurred. Chapter 6 opens with that uncertainty. It is the space between physics and intent, the thin atmosphere where serious speculation tries to breathe. For the first time in decades, mainstream astronomy and UFO research shared a narrow overlap, data that refused to be comfortably simple, yet declined to be extraordinary. Several teams now worked backward through the data, building simulations of trajectories that might produce the observed behavior. Some found models that worked only if the body were unusually flat. Others required an internal density so low it resembled aerogel. The conversation turned philosophical. Was nature truly capable of forming such an object? Or were we seeing the signature of an intelligent fabrication, an interstellar probe, or debris from one? The claim was not that aliens had visited. It was that a non-terrestrial technology could leave fingerprints even if the machine itself never survived. We call those traces technological residues, patterns that imply engineering even when the artifact is gone. For example, if a body maintains constant acceleration without mass loss, something must be pushing. Radiation pressure alone would need a reflective surface of a specific ratio, thin, wide, and deliberate. One group at the University of Cambridge coined a term for this investigative method: forensic astronautics. It meant studying distant anomalies the way archaeologists study ruins, by inference, pattern, and process of elimination. Every unexplained vector or emission was treated like a shard of pottery, not proof of culture, but evidence of process. A separate team in Kyoto took a more direct approach. They used machine learning to trawl through historical comet data, teaching algorithms to recognize hyperbolic visitors whose non-gravitational parameters deviated from the norm. Dozens of candidates appeared, all dim and short-lived, all quietly erased from public curiosity by the passage of time. What if, they asked, this was not the first artificial traveller, only the first one bright enough to catch our attention? That question sent ripples through institutions. NASA issued a calm statement emphasizing natural explanations. The European Southern Observatory called for restraint and reproducibility. Harvard's Avi Loeb repeated his earlier argument, that the burden of proof should not rest solely on the extraordinary hypothesis, but on the completeness of the ordinary one. If conventional physics can explain all signals, fine, but if not, then science must be brave enough to look beyond habit. Public response split into familiar camps. Skeptics pointed to modelling errors, while believers called it vindication. But in laboratories, where the air hummed with data rather than opinion, researchers quietly drafted new mission concepts. What if we could send a small probe to intercept the next interstellar object before it left? The idea was not fantasy anymore. Advances in solar sails, compact sensors, and autonomous guidance made it plausible within a decade. The proposed mission had a pragmatic name: Sentinel. It would park in an orbit near Venus, where sunlight is strong and response times short. When the next interstellar body is detected, Sentinel would unfurl its sail, catch the radiation, and pursue. Its instruments would include a miniature spectrometer, a thermal imager, and a wideband radio receiver tuned for narrow signals between 1 and 12 GHz. In short, it would look and listen without assumption. Behind the scenes, engineers debated the right threshold for triggering an intercept. Was any hyperbolic trajectory enough, or only those with high eccentricity and stable acceleration anomalies? Some argued for statistical triggers, others wanted human oversight. The compromise, both. Algorithms would flag, humans would decide. The lesson from 3i Atlas was that enthusiasm without calibration breeds confusion. A quieter debate emerged in ethics forums. If one day we did detect engineered material, what would we owe its makers? Do we treat it as property, evidence, or artifact? Could we touch it, or would doing so risk contamination, biological, cultural, or informational? Philosophers of science began drafting protocols of contact that sounded at times like new chapters in maritime law. Meanwhile, evidence collection continued. High-altitude observatories reprocessed the infrared data, looking for any spectral tail that could hint at manufactured alloys. Nothing conclusive appeared, yet the residuals were oddly persistent. A 2% deviation in reflectance around 0.9 micrometers, right where certain ceramics peak. Enough to keep the hypothesis alive, not enough to crown it. In parallel, a SETI-adjacent group at the Allen Telescope Array launched an experiment called Echo Sweep. They beamed faint broadband pings toward the region where the object had been months earlier, then listened for any reflection inconsistent with dust or plasma. Most of what came back was static. But once, only once, a narrow spike drifted across the spectrogram in a way that made even hardened engineers pause. It was not proof. It was, however, beautifully timed. The spike crossed precisely when Earth's rotation brought the array into the plane of the former trajectory. The team spent weeks proving it was local interference, but doubt had already nested in their minds. That single blip reignited debate over intent versus coincidence. How many coincidences does it take to mimic communication? How often does nature send pulses that look engineered but are not? The answer is statistical, not emotional, and so the data were fed back into Bayesian models, where prior probabilities battled new likelihoods. The resulting number, 1 in 1200 chance of coincidence, meant little to the public but everything to the analysts. It said, interesting, but not extraordinary. Late in the year, 2 new comets entered Discovery catalogues, both inbound, both with slightly hyperbolic signatures. Neither matched the original's trajectory, but both triggered old instincts. The Sentinel design team began rehearsing on simulations, refining intercept windows. They built training scenarios labelled natural, ambiguous, and intentional. Each scenario forced the algorithms to justify their classifications, an exercise meant to prevent both false excitement and premature dismissal. The UFO hypothesis was not treated as fringe here. It was simply one branch on a tree of explanations, pruned by data. The tone was sober. If an intelligent origin ever revealed itself, we would see it first in math, not mythology. An equation balanced, a drift repeated, a ratio locked. The truth would look like a pattern that refused to go away. In that calm, analytical light, even skeptics found themselves curious. Not believers, but participants in a conversation larger than ridicule. They admitted, the universe is big enough for surprises, and human models are small enough to miss them. Between those truths lies the space where discovery hides. As this chapter closes, the speculative frame remains open. The green traveller is gone, but the idea it carried persists. That intelligence may express itself through structure rather than speech, and that silence may contain design. We are not finished investigating. We are learning how to ask better questions. The next visitor, if there is one, will meet instruments calibrated not for belief, but for proof. We end, as all good investigations should, with the list still on the wall, what would change our minds. One narrow tone, one thermal curve that disobeys sunlight, one geometry that refuses chaos, one motion that cannot be vented away. 4 simple ways the universe could whisper, look closer. Until then, we listen. Not to confirm a fantasy, but to prepare for the day it is no longer fantasy at all. Hypothesis retained for next analysis cycle does not mean we are padding time. It means the case file stays open under stricter rules. From this point, the plan is operational rather than poetic. We convert speculation into checklists, and checklists into instruments. The first instrument is policy. Write, in public, the exact conditions that would elevate the UFO interpretation from interesting to compelling, and the exact datasets that could falsify it. No moving goalposts, no post hoc victories. The second instrument is geometry. We replay the trajectory with updated astrometry and recompute non-gravitational parameters using competing thermal models: slow rotator, fast rotator, and mixed. We bound jet geometry by asking a blunt question. What vent placement and output would reproduce the residuals with the fewest assumptions? If a single vent family explains the curve, technology loses a chip. If residuals remain orthogonal to sunlight after that effort, the chip moves back. Third comes rotation state. We segment the light curve into week-long windows, fit periods independently, and test for stepwise torque events. Any discontinuity must survive 3 checks. It must appear in multiple apertures, it must align with no instrument temperature swings, and it must persist when we mask suspect frames. A putative control input that fails any check is reclassified as thermal breathing. A candidate that passes escalates to targeted follow-up in the next object we intercept. On radio, we switch from opportunistic listening to templated pursuit. Drift models are generated not only for Earth's motion, but also for transmitter behaviors, stable clock, aging oscillator, and deliberate frequency hopping. For each template, we compute the likelihood of seeing a line with the observed slope and width. We then run the same search on off-target sky to estimate false positive rates from satellites and harmonics. If an on-target line survives subtraction and the off-target baseline, the pipeline pauses human attention instead of social media. Meanwhile, the Sentinel team tightens its design. The sail geometry is locked to a square of thin film with variable reflectivity, enabling thrust modulation without moving parts. The payload list stabilizes: a compact infrared spectrograph for volatiles, a visible spectrometer for metals, a microbolometer for thermal mapping, and a wideband radio receiver with a disciplined clock and raw voltage capture. Nothing fancy, just enough to discriminate between dust, design, and wishful thinking at a single high-speed pass. Trigger policy becomes explicit. A hyperbolic discovery with eccentricity above a published threshold immediately seeds a watch state. If subsequent photometry shows stable non-gravitational acceleration after solar angle correction, the state upgrades to intercept. A small committee with members from independent institutions has 24 hours to veto. Silence equals go. The point is not to guarantee drama, it is to guarantee data while the window still exists. Ethics is not an afterthought. If Sentinel meets hardware that looks unambiguously manufactured, the protocol is to image and sample only the surrounding dust, not to collide or capture. Ownership is undefined, contamination is forever. We gather photons, not trophies. The archive gets a second life as well. We run a retrospective sweep on past hyperbolic candidates, pushing the same disciplined templates through years of quiet detections. The goal is not to retcon triumphs, but to measure how often nature generates shapes and drifts that tease intelligence. If the false positive rate is higher than we thought, we tighten thresholds. If lower, we breathe easier about calling the next anomaly what it is. There is also the matter of materials. A small consortium builds a chamber where micron-scale grains can be cycled through intense heating and cooling in high vacuum, while their spectra are recorded in the same band Sentinel will carry. Nickel-doped ices, carbon-rich silicates, exotic ceramics, all are tested. The idea is simple. If a line appears in space, we want a library on Earth that can say, "You have seen this before." Nature deserves the first chance to explain herself. As results roll in, the decision tree narrows. The outbound brightness stability that worried us now sits comfortably within models that include large grain dominance after perihelion. The reflectance kink near 0.9 micrometers shrinks when we apply a revised flat field to one instrument's late-season data. The torque micro-events disperse when we widen the window and apply stricter outlier controls. None of this is a defeat. It is the earned satisfaction of removing mirages from the map. Chapter 7. The signal that wouldn't stay silent. By the time Sentinel's first calibration images arrived, the quiet optimism of the scientific community had sharpened into disciplined vigilance. The green visitor had left behind not only data but a blueprint, a method of readiness that had transformed speculation into standard practice. The age of passive wonder was over, the age of forensic observation had begun. The mission controllers in Pasadena kept their voices low. Screens showed the sail's shimmering square unfolding against the black, sunlight glancing off its mirrored film. The craft was functioning exactly as designed. Every reaction wheel, every gyroscope, every radio clock ticked within expected margins. Yet, in every pause between telemetry updates, someone inevitably asked the same question in a different form. What will we do if it isn't just another rock? That question wasn't fantasy anymore. Sentinel had a clear protocol, derived from the lessons of 3I Atlas and its ambiguous kin. It would measure first, compare second, speculate last. And yet the very existence of that order implied the one thing every scientist secretly hoped for, that there might come a day when speculation would need to become action. The first few weeks were routine. Sentinel's instruments mapped solar wind gradients, tested radiation shielding, and cross-checked sensors against Earth-based telescopes. The sail's stability in sunlight was remarkable, drifting only fractions of a degree per day. Its velocity aligned beautifully with mission models. The team grew confident that the craft was ready. Then, one morning, telemetry from the onboard dust analyzer showed something strange. A cluster of impacts that didn't match the expected grain size of the interplanetary medium. The data suggested angular fragments. Thin, layered, metallic. A few joked about lost paint flakes from old missions, but when the same pattern appeared over multiple readings, the tone shifted. Engineers ran contamination models. Nothing from Sentinel's own body fit the spectrum. The fragments moved faster than expected for debris, and slower than for micrometeoroids. Their direction suggested an intersecting stream, not random distribution. A small note appeared in the mission log. Possible engineered microstructure. It wasn't an announcement, it was an invitation for restraint. On the ground, analysts cross-referenced orbital dynamics. The fragment's trajectory traced back to a diffuse cloud intersecting the ecliptic plane, a region flagged months earlier for weak radar echoes. No object large enough to cause it had been found. The radar team nicknamed it the Ghost Wake. Sentinel's readings gave it substance. Within days, observatories retasked telescopes to survey the region. Nothing visible emerged, but faint radio scatter hinted at a structure. A long, low-density field reflecting signals in a pattern too regular to be random. The best models described it as a sheet, tens of kilometers across, paper-thin and tumbling gently. The word artifact slipped into the discussion, first whispered, then typed in cautious memos. Protocol required restraint, so the Sentinel team ran through the checklist. Could radiation pressure alone organize dust like that? Possibly, but the geometry would need tuning nature rarely achieves. Could electrostatic forces? Unlikely, given the coherence length. Could coincidence? Always possible, but coincidences don't often repeat at orbital scale. As reports accumulated, the project's independent review board convened. Their tone was calm, procedural. Each hypothesis was logged, scored, and assigned a confidence rating. Artifact hypothesis began at 3%, barely above noise, but every new dataset nudged it upward. The press knew none of this. The public saw only the launch photographs and the crisp blue animations. Behind the curtain, probability was climbing like a slow sunrise. Then came the signal. Not a beacon, not even a tone, just a persistent band of noise that shouldn't have been there. Narrow, drifting slightly, repeating across Sentinel's receiver in intervals of 92 seconds. It could have been a local oscillator fault, except the redundancy unit showed the same pattern. A soft tremor of excitement moved through the control room. No one spoke the word communication, they just said, "Run verification." Verification took 12 hours. Ground stations across 3 continents rechecked frequencies. Off-target tests returned silent. On-target recordings confirmed the drift matched no satellite, no pulsar, no known cosmic source. The team led, Dr. Kiran Shah, logged the result with the same phrase used for the Atlas-era anomalies, unexplained under current models. The next debate was procedural, announce or confirm. The board chose confirmation. Announcements come with speculation. Confirmation comes with math. Over the next 3 days, they compared the signal's drift rate to potential dynamics. The rate matched an object roughly 1 astronomical unit away, moving outward at 38 kilometers per second, faster than any known comet, slower than any radar artifact. Publicly, nothing changed. Privately, Sentinel had become history's most carefully monitored whisper. Analysts checked solar wind conditions, radio interference from Earth, and thermal oscillations from the sail. Nothing explained the persistence. The amplitude stayed steady, as if the source were broadcasting not power, but precision. Theories multiplied. One group suggested the signal came from an old probe, perhaps a relic of our own civilization reflected back from interplanetary plasma. Another proposed a natural maser effect amplified by dust alignment. A third hinted at intentionality, but offered no mechanism. Dr. Shah summarized it simply. Everything fits, except the comfort of our assumptions. Days turned into weeks. The signal faded, returned, and faded again. Always on the same interval, always within the same narrow band. Each reappearance forced another round of verification. No one declared discovery. They only expanded the definition of anomaly. To test the geometry, Sentinel rotated its sail slightly, using the edge as a radio reflector. The maneuver modulated the received strength, confirming that the signal's direction was external, not internal. A quiet gasp ran through the comms team. They were seeing, perhaps for the first time, a phenomenon interacting directly with a human-built instrument beyond Earth's orbit. The reaction within the community was split. Half argued for patience, the other half for boldness. Should Sentinel broadcast a simple pattern back, a prime sequence, a geometric pulse? The ethics board said no. Until intentionality was proven, no message should be sent. The risk wasn't danger, it was contamination of evidence. Science's first rule had always been, observe before speaking. Meanwhile, the signal's signature began to change. Its drift slowed, then reversed slightly, as if the source had altered velocity. A coincidence? A calibration artifact? Or an answer? The math was too delicate to decide. The analysts published preliminary findings under the neutral title, Narrowband Drift Consistency and Solar Wind Interference. Only a few insiders knew how much weight those words carried. Back on Earth, public curiosity rekindled. Amateur astronomers noticed the hush from official channels, and began digging through open databases. Some found the drift logs and posted them online. Forums lit up overnight. Theories ranged from malfunction to message to mirror probe. By the time Sentinel completed its rotation sweep, speculation had escaped containment. Facing mounting attention, the review board authorized a press release, short, factual, and careful. It confirmed the detection of a repeating radio feature of natural or instrumental origin pending verification. The statement was technically accurate and emotionally evasive, but Curiosity had already crossed orbit. Within weeks, new instruments were pointed toward the source region. The James Webb Space Telescope captured faint infrared glints, consistent with a semi-reflective sheet. ESA's solar orbiter detected small but regular plasma perturbations passing its sensors. The pattern looked less like dust and more like modulation. The evidence grew coherent. Dr. Shah's final briefing to the mission control staff was characteristically understated. We can explain almost everything we see, but not quite everything at once. It was the most honest summary of the unknown since the first interstellar visitor entered our record. As this chapter closes, the question no longer feels theoretical. It feels procedural, like a new kind of astronomy taking shape. An astronomy that doesn't look for confirmation of life, but for the statistical fingerprints of intent. The silence between signals is no longer emptiness, it's the control in an experiment we are still learning how to run. The next phase will not chase miracles, it will test persistence, coherence, and reproducibility, the same virtues that turned myths into models. If one day the signal stabilizes, or the sheet responds to solar flares in deliberate rhythm, we will be ready, not to believe, but to measure. And if nothing happens again, the method remains. That is the quiet victory of the scientific kind. The last entry in Sentinel's log for that month reads simply, data stable, origin unknown, observation ongoing. A statement that could belong equally to astronomy or to philosophy. Perhaps the difference between them is not certainty, but patience. All analysis pipelines remain open to replication. An audit is not a slogan. It is the backbone of what happens next. The team circulates the code repositories, frozen with comet hashes, along with raw voltage snippets and exact tuner states for the narrowband feature. External groups are invited to run the pipeline and try to break the claim. The point is not consensus, it is reproducibility. With outside eyes engaged, Sentinel switches modes from survey to characterization. The sail rotates in small steps to map the angular dependence of the signal strength, creating a crude beam pattern. The result is asymmetric, peaking 5 degrees off the estimated source line. That offset matters. It lets engineers model the sheet-like reflector hypothesis with real geometry rather than guesswork. Light curve watchers on Earth contribute in parallel. Although the source is radio, optical teams search for correlated microglints, millisecond spikes that could be reflections from flat facets as the sheet tumbles. After weeks of null results, one array logs 2 glints 40 minutes apart, at angles consistent with the radio offset. Coincidence is possible, correlation is better. The data go into the joint fit. The drift behavior is the next target. Analysts segment the 92-second recurrence and fit microslopes to each epoch. The slopes are not identical. They cluster around 2 values that flip every few hours. Thermal flexing in a natural sheet could do that. So could a system that alternates between 2 timing sources. The hypothesis remains bifurcated. Physics versus intent, both viable, neither triumphant. To sharpen the distinction, Sentinel executes a solar wind provocation. During a forecasted high-speed stream, the craft holds attitude and records continuously. If the sheet is passive, the signal's strength and drift should respond smoothly to plasma pressure changes. If it is active, the response could be buffered or discretized. When the stream arrives, the drift wobbles, small, smooth, nearly textbook. The active hypothesis loses a little probability mass. Not gone, just lighter. Ethical questions surface again. The temptation to transmit persists, especially among those who see the alternating drift as a primitive handshake. The board reiterates the rule, observe before speaking. It adds a corollary, if an unmistakable address header appears, a prime grid, a Barker code, an error-correcting preamble. The policy can be revisited within hours. Until then, silence is methodology. Materials labs deliver their first useful comparison. Nickel-doped amorphous ice grown in vacuum, then flash-heated, reproduces a shallow reflectance bump near the band of interest, and produces flakes with edges sharp enough to mimic engineered fragments. That result shifts the balance toward natural origins for the dust seen by Sentinel earlier. It does not settle the radio question, but it removes a prop from the artifact stage. Public communication adapts. Rather than a single dramatic announcement, the project posts a living document of what would change our minds, including live confidence intervals. The list is short and operational. 1. A stable narrow tone with predicted Doppler drift surviving off-target subtraction. 2. Geometry that holds symmetry across rotations for weeks. 3. A thermal curve out of phase with insulation repeatably. 4. A velocity change pointing into shadow after vents should be cold. Chapter 8. The discipline of wonder. The story ends not with discovery but with discipline. Sentinel continues to orbit the sun, its sail dim against the solar wind, its instruments recording steady telemetry that seems almost uneventful. But uneventful is the point. For the first time, humanity has built something that listens without bias, an instrument whose patience outlasts curiosity. In the months since the narrowband signal faded, the mission has settled into rhythm. The radio receiver cycles through quiet bands, the spectrograph rechecks volatile ratios in passing dust, and the guidance system holds position with graceful precision. Nothing spectacular happens, yet every byte is valuable. Each uneventful hour teaches calibration, tolerance, and humility. Public attention has moved on, but within the small world of interstellar research, the work feels alive. Teams across continents refine their models, correcting for subtle plasma effects and newly discovered correlations between solar wind fluctuations and minor drift. Most of the anomalies now yield to physics. The rest remain annotated, open for re-examination when better instruments arrive. This is what maturity looks like in science, when excitement transforms into stewardship. The field has learned to resist the reflex of conclusion. A decade ago, a repeating signal might have been declared extraordinary. Now it is archived, logged and tested against null hypotheses until the mystery either survives or dissolves. Still, one mystery endures. In Sentinel's data, a residual pattern remains, so faint that it lies at the edge of noise. It appears once every few weeks, offset by a predictable phase relative to the sail's rotation. Some analysts believe it's internal resonance, others think it's geometry interacting with the magnetic field. A few quietly wonder if it's a trace of the phenomenon itself, a postscript written in plasma. No one calls it proof, no one dismisses it either. Instead, the mission team does what good scientists do. They improve the model, document the uncertainty, and keep the log open. Origin under evaluation, the status line reads, as if it were a mantra for the species. What began as an investigation into a comet-like object has evolved into a new branch of astronomy, an astronomy of anomalies. This field has no single instrument, no single theory, only an attitude, that surprise is not an error but an opportunity. Whether the surprise leads to alien engineering, exotic physics, or simple misinterpretation matters less than the process itself. In universities, new courses appear under titles like Interstellar Object Dynamics and Techno-Signature Forensics. Students study the case of 3i Atlas as if it were a historical event, dissecting its data with better algorithms than the original team ever had. The point isn't to find a new conclusion, it's to learn the posture of skepticism that welcomes wonder without surrendering to it. For the broader public, the lesson is subtler. We are learning how to live with cosmic uncertainty. Once, mystery demanded myth. Now, it demands patience. The frontier no longer glows with danger or divinity. It hums quietly with instrumentation. The cosmos feels no smaller for this. If anything, it feels closer, more conversational. The idea of communication has changed too. Scientists speak now of environmental signaling, a term for patterns that convey information without intention. The cosmos might not speak to us, but it leaves artifacts of behavior that we can read like weather. A magnetic fluctuation here, a thermal anomaly there. They tell us about the universe's temperament, even if not its mind. Some still dream of a clear message, a pulse, a sequence, a code that could end the debate forever. Perhaps that will come. but those who have spent years in this work suspect the truth will be quieter. Intelligence, if it exists elsewhere, might not broadcast. It might prefer to be inferred rather than heard, leaving behind only the evidence of design in motion. Dr. Shah, whose team first logged the repeating drift, describes it this way: "We've learned that listening is not waiting, it's participation." Under her leadership, Sentinel has become less of a probe and more of a presence, a reminder that curiosity, properly structured, is an act of endurance. Beyond Sentinel, other missions are now forming. A twin sail, codenamed Horizon, will launch within the decade, designed to patrol the outer heliosphere. A small fleet of micro-interceptors, built to hitch rides on other missions, will wait in standby for the next hyperbolic visitor. The infrastructure of curiosity is expanding piece by piece. The shift is cultural as much as technical. Governments fund these missions not out of spectacle, but strategy. Understanding interstellar objects now means understanding the flow of material and perhaps technology between systems. Cosmic traffic, once a poetic phrase, has become a matter of planetary security and philosophy alike. Even skeptics, once dismissive, have adapted. The UFO debate has matured from argument to methodology. The question is no longer, is it aliens? But what would it take to know either way? That single pivot has moved the discussion from television to textbooks. The extraordinary has become measurable, and that is its own quiet revolution. In one of her last public talks before retiring, Dr. Shah told an auditorium of students, "Science is not about believing less. It's about believing later, after the evidence has done its work." The room was silent for a moment, then broke into applause that felt more like agreement than admiration. Outside the world of academia, people still look up. The public tracking dashboards for interstellar candidates now have millions of subscribers. Children click through nightly sky maps, looking for small arrows labelled possible visitor. When they ask what happens if one turns out to be real, the best answer might be, we'll measure it carefully. And if one day a real message comes, a tone, a pulse, a geometry that resists explanation, it will meet a civilization that has practiced patience. We will not panic, nor worship, nor deny. We will log, confirm, replicate, and learn. It may be the slowest form of greeting imaginable, but it will be honest. In that way, 3i Atlas did more than bring data. It brought rehearsal. The comet that wasn't quite a comet reminded us how to listen and how not to leap. It trained an entire field to keep wonder and restraint in the same orbit. The last transmission from Sentinel before its solar conjunction reads simply, "Nominal signal, observation continuous," a line that could describe both the spacecraft and the species that built it. The rest is silence, the kind that listens back. Every dataset becomes a calibration point for the next generation of missions, and the data that once seemed extraordinary now serves as baseline. Sentinel's records are no longer seen as anomalies, but as training material for instruments that will be sharper, faster, and more patient. This is how discovery matures, by converting excitement into infrastructure. The next generation of missions takes this lesson to heart. Horizon, the twin sail now in late assembly, incorporates every improvement learned from Sentinel: better shielding, adaptive reflectivity, and a precision clock synchronized by quantum link. It will drift farther than any human-built object powered only by sunlight. Its mission is not to chase, but to wait, to patrol the heliosphere's edge and listen where the noise thins. Across observatories, the same cultural shift is visible. Data teams publish not just their conclusions, but their null results, their calibration files, their mistakes. Reproducibility becomes reputation. Conferences open with transparency reports rather than grand claims. The UFO hypothesis, once a battleground of belief, has been converted into a method of exclusion, a way to test nature until it stops surprising us. Paradoxically, that makes real surprises more credible. In classrooms, students debate not whether we are alone, but how we would know if we were not. They simulate signal detection pipelines and practice falsification drills the way earlier generations practiced fire drills. The lesson is that skepticism is not cynicism, it is maintenance. It keeps instruments honest and imaginations aligned. The public, too, has adapted. News cycles still flare whenever a new interstellar candidate appears, but the tone is calmer. The questions are sharper. What are the error margins? How was the drift modelled? Where are the raw files? Citizens have learned to read scientific appendices as if they were mysteries, passing confidence intervals like plot twists. It is a new kind of literacy, the literacy of uncertainty. Back in Mission Control, Sentinel's telemetry scrolls on. The spacecraft's sail catches sunlight with steady elegance, its sensors aging gracefully. The team that built it has changed. New graduates now manage its data. They treat it like a colleague, not a relic. The daily logs are brief. Signal nominal, background stable. To an outsider, that might look like monotony. To the insiders, it is serenity, the confirmation that method still holds. Once, the team expected a revelation. Now, they understand that the revelation was procedural, how to build an experiment that can coexist with wonder. Science had to learn to speak the language of patience before it could hope to hear the language of the stars. Months later, a faint echo appears in Horizon's commissioning tests, a narrow feature hovering near a frequency Sentinel once logged. It is weaker this time, barely above noise. The team reruns the calibration chain, tests every antenna gain curve, and repeats the observation 3 times. Each time, the feature fades but never vanishes completely. The similarity is tantalizing, but the verdict is familiar. Unconfirmed. Insufficient evidence. No one seems disappointed. The engineers smile, the analysts nod. They know the real success is the speed of their discipline, the swiftness with which they can separate the measurable from the mythical. In that efficiency lies a new kind of beauty, the elegance of being prepared for the unknown without being consumed by it. The culture that grew around Sentinel and Horizon is starting to influence other sciences. Climate monitoring, particle detection, and deep ocean acoustics borrow its principles of open calibration and shared falsifiers. The logic is contagious. Measure carefully, publish quickly, let the evidence be communal. The frontier of curiosity has widened, but it has also grown more stable. As this final stage unfolds, the UFO hypothesis takes on a humbler, nobler role. It is no longer an argument, it is a control variable. It reminds every analysis that imagination has a place, provided it knows its limits. It ensures that science remains wide-eyed without being blind. And still, the mystery lingers, not in the data, but in the act of listening itself. Somewhere beyond the heliopause, sunlight falls on dust that once passed through other systems, carrying atoms forged in unknown stars. Each grain is a record of motion and origin. Each silent particle is proof that the cosmos has been busy long before we arrived to witness it. Dr. Shah, retired now but still writing, ends her final paper with a line that reads like poetry disguised as documentation. We have not yet found evidence of intention in the cosmos, but we have found evidence of readiness in ourselves. That readiness, patient, procedural, collective, is perhaps the most significant discovery of all. When the archives of this century are reviewed, the first age of interstellar investigation will not be remembered for any single signal. It will be remembered for the moment humanity decided to stay calm in the face of possibility, for the shift from spectacle to stewardship, for the quiet confidence that the universe does not need to surprise us to remain magnificent. The final log entry from Sentinel, transmitted before its systems are powered down for cruise mode, reads, "Observation complete, data archived." A message so simple it feels ceremonial. Somewhere in the understatement lies the heart of our species, a desire to witness, to record, to understand without owning.